Four cars travel along the same road, one at 51 miles per hour, another at 88, the third at 42, and the last at 135. If I asked you to choose a value that represents the average of these speeds, which one would you pick? You might add them up and divide the sum by 4, getting 79 miles per hour. This is the classic way of computing the average. But is it really the most meaningful? Let me show you another one. Imagine placing the cars in a relay race and asking, what constant speed would allow us to cover the entire distance in exactly the same total time as the four cars together? In this case, the answer is no longer 79. It is about 64.3. Where does this number come from? What other ways of taking the average exist? And do these ways lead to very different results? This video answers those questions. If you enjoy it, give it a like and don't forget to subscribe to the channel. Ready? Let's get started. Let's begin by clarifying what we mean when we say to take the average. Take the four initial speeds and represent them with a bar chart. Now try to level them as if they were tower of bricks moving blocks from one column to another. When all the columns have the same height, that height is 79. In other words, 79 is the number that repeated 4 times and added together gives the same result as adding 51, 88, 42, and 135. More generally, for n data values x1, xn, the classical mean m is defined as the value for which x1 plus x2 until xn equals the sum of n copies of m. And here comes the generalization. Why should we always use addition? In other contexts, it might make sense to use different operations. Let's denote a generic operation by star. We could define a mean based on star as the value m that, repeated n times with the chosen operation, produces the same result as applying star to the original data. This definition may not always yield a meaningful m, but it allows us to see that if we use addition, we get the classical mean, whose full name is the arithmetic mean. If we use multiplication instead, we get another formula, the geometric mean, widely used in economics. To avoid complications, from now on, we assume the data are positive, so that existence and uniqueness are not an issue. There are infinitely many possible operations we could choose, but there is still one worth mentioning, based on the sum of reciprocals. This is the harmonic mean. It may sound odd, but it has concrete applications. Remember the opening problem about speeds? Well, the average speed of 64.3 miles per hour across the whole trip is exactly the harmonic mean of the initial speeds. The arithmetic mean A, the geometric mean G, and the harmonic mean H are three very important types of average, and they have some good properties. They are symmetric in the axis, so they do not depend on the order in which the data are collected. Their value always lies between the smallest and the largest data point. They scale naturally with the data in the sense that if you multiply all data by a positive value c, the means are also multiplied by c. If one of the data values increases, the means also increase. Finally, they are stable, meaning that the mean m does not change if you add m to the initial data. The proofs follow from simple algebraic steps, but in this video I want to show you a different property that links these three means together. Regardless of the dataset, we always have h less than or equal to g less than or equal to a. There are many proofs of this famous inequality, but most of them are rather complicated and often rely on other inequalities such as Jensen's. I want to give you an easier proof, inspired by Cauchy's method, with a few simplifications. First, let's look at the inequality graphically. Consider the case of just two data values, x1 and x2. Represent them as a point in a horizontal plane. On the vertical axis, we place the value of the means. For the arithmetic mean, take the point x1, x2 and move vertically to the height x1 plus x2 divided by 2. As x1, x2 varies, these points form a plane, here shown in blue. In the same way, we can build the surface of the geometric mean in purple and the harmonic mean in red. It is clear that the red surface lies below the purple one, which in turn lies below the blue one. This corresponds exactly to the inequality h less than or equal to g less than or equal to a. Near the origin, you might think the surfaces cross, but that is just a rendering artifact. With two data values, it is actually not difficult to prove the inequality rigorously. You expand the square, which is always non-negative, and conclude with a few algebraic steps. If the proof is easy for two values, the same cannot be said for a general number n of values. One might try induction, but it would still be a bit heavy for beginners. The mathematician Cauchy found a nice simplification of the inductive proof, which works when the number of data points is a power of 2. Of course, the number of data points is not always of that form, but there is a trick to get around it. Suppose we have proved the statement in Cauchy's form, namely for datasets with sizes that are powers of 2, and now we consider a set x1, xn. Let h be its harmonic mean. Add h to the set repeatedly until the total number of elements becomes m, a power of 2. By stability, the harmonic mean of this new set is still h. Since this set has a size that is a power of 2, we can apply Cauchy's forms of the inequality and conclude that h is less than or equal to the geometric mean of this extended dataset. Write out the definition of the geometric mean and separate the original data from the added h's. Now, take the inequality obtained, raise both sides to the power of m, rewrite the product of the original data in terms of their geometric mean, and divide everything by h to the power of m minus n. Extracting the nth root yields h less than or equal to g. To prove that g is less than or equal to a, the same method works, but starting with the arithmetic mean a. I leave that part as an exercise. With that in place, all we need is to prove the inequality for sets whose size is a power of 2. For a single value, the proof is trivial. For 2, we have already seen it. What remains is the inductive step. Suppose the inequality holds for sets of size 2 to the power of n. We want to prove it for sets of size 2 to the power of n plus 1. Group the data into 2 to the power of n pairs and compute for each pair their geometric mean, small g. The geometric mean of the original set can then be rewritten in terms of these small g's. In fact, it is the geometric mean of the set of g's. Since this set has size 2 to the power of n, the inductive hypothesis applies. Denote by small a the arithmetic mean of the pairs, and by small h their harmonic mean. Since these means are computed on two values, we know that each small h is less than or equal to its corresponding small g, which in turn is less than or equal to its corresponding small a. Since larger data values correspond to larger means, we can assert that the harmonic mean of the h's is less than or equal to g, which is less than or equal to the arithmetic mean of the a's. A few algebraic steps show that the first term corresponds to the harmonic mean of the original set. While the last term corresponds to the arithmetic mean of the original set. Which completes the proof. Had we been more precise in the previous argument, we would have noticed that the inequality is always strict except when all the data values are equal to one another. This is also clear in the graphical representation with two data points x1 and x2. The three surfaces are well separated and touch only along a single line, which corresponds to the case x1 equal to x2. This means that the inequality is strict except for identical initial data, in which case the three means coincide. To avoid confusion about the order of the three means in the inequality, here is a useful way to remember it. For an integer p not equal to 0, we can introduce the mean mp through this formula. This formula generalizes the arithmetic mean, which corresponds to p equal to 1, and the harmonic mean, which corresponds to p equal to -1. It's not trivial, and we will not prove it here, but it's true, that the geometric mean corresponds, as a limiting case, to p equal to 0. In this language, the HGA inequality becomes m-1 less than or equal to m0 less than or equal to m1. And it does not stop here. Continuing with other values of p, we obtain an entire family of means, ordered among themselves, with inequalities that are much easier to remember. The quadratic mean m2 has special relevance, although we have not covered it today. We will talk about it in a future video. One last important thing to know, and here I will conclude, is that this chain of inequalities can be reversed by introducing suitable constants that depends on the number of data n. This means that in a sense, these means can't be too far apart from each other. If you enjoyed the video, remember to like and subscribe. Thank you, and in the meantime, don't panic.